Let's spice things up a bit. So far, we've been focusing on the simple linear regression model that only had one sort of input variable, x. We will now start looking at models that allow us to utilize multiple input variables. But before we get there, there's some terminology that I wanted to establish. In the context of linear regression, there are many equivalent terms that are used, and this slide sort of outlines all of them, and you should be familiar with each of these equivalent definitions for our purposes. So our input variables, x, often go by the names features, covariates, independent variables, explanatory variables, predictors, inputs, and regressors. All of those things refer to our x, or our inputs. Other names for our y values include outputs, or outcomes, or response, or dependent variables. And so other names for y hat, or predicted y values, could be predicted outcomes, or predicted responses, or predicted dependent variables, and so on and so forth. So if you ever get confused about the terminology that we use in regression, come back to this slide and hopefully it will make some things clear. Now, let's suppose we want to add independent variables to our model. Right now, our model looks something like theta naught plus theta 1x, and we call these quantities, theta naught and theta 1, parameters. But other names that these quantities can go by are coefficients or weights. And so we might say that theta naught is the coefficient on the intercept term, or of the intercept term, and theta 1 is the coefficient on the x term, or the weight of the x term. So if you hear parameters, coefficients, and weights being thrown around, those are all referring to the same thing for our purposes. So let's suppose we want to add independent variables or features to our model. A linear regression model with two features might look something like this. Y is equal to theta naught plus theta 1 times x1 plus theta 2 times x2. So what's different between this and our simple model? Well, our simple model only had a single x and it had two parameters, theta naught and theta 1. This new, more sophisticated model has two input variables, x1 and x2, and it has three parameters, theta naught, theta 1, and theta 2. Two of those parameters are the weights on the x's, so theta 1 is the weight on x1, and theta 2 is the weight on x2, and then we also have our intercept term, theta naught. Let's consider an example using basketball data. Now in basketball, some statistics that we are interested in include the number of points that a player averages, the number of assists or passes that a player averages, and the number of three-point field goal attempts that they make. For instance, let's suppose we want to predict the number of points per game that a player averaged over a season. One model that we could build is to predict points just using the number of assists that player averaged in the season. And so, doing so might yield a model that looks like 3.98 plus 2.4 times their assists. If we instead want to increase the sophistication of our model and instead use both the number of assists that player averaged and the number of three-point field goal attempts that they averaged, our model might look something like 2.163 plus 1.64 times assists plus 1.26 times three-point attempts. Now you can see our prediction function now includes two independent variables, or two features, assists and three-point attempts. For now, we will abstract away the process of actually determining the optimal coefficients when we have any more than one independent variable. This will be the focus of the next lecture, but just know that these were sort of derived the same way that the coefficients in the simple regression case were defined, which is by minimizing average squared loss. Let's visualize what these models look like. So on the left, we have a scatter plot of assists on the x-axis and points on the y-axis. So the blue points correspond to the true observations. And this red line corresponds to our simple linear regression model, 3.98 plus 2.4 times assists. Our new sophisticated model has two independent variables, and so it looks like a plane in 3 dimensions. So we have one axis for assists, so one of our independent variables. We have another axis for 3-point attempts, and our height, the z-axis, is the number of points that we predict that they averaged in the season. These blue points over here correspond to true observations. So our data set had some players in it, and we have the number of assists, 3-point attempts, and points that they averaged, and this is what that is a plot of. And this plane that's orange purpley is our prediction function. This is our model that we established over here on the last slide. And if you want to, you can play around with this visualization in the companion notebook, but that's not really the point of this video. More generally, the multiple linear regression model is of the form theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, so on and so forth, until theta p xp. You can rewrite this in terms of a sum, theta naught plus the sum of theta j times xj, where j goes from 1 to p. And here, xj refers to feature j, not data point j. So you remember before, when we looked at expressions of mean squared error, we had yi minus yi hat. There, that index I referred to, data point I, so like the 3rd observation or the 10th observation. Here, j refers to the features. So the model that we looked at before had 2 features. x1 was assists, and x2 was 3-point attempts. Now, we would say that this model has p features plus an intercept term. Depending on the context, this will either be described as being p features or p plus 1 features, but we will try and make that clear when sort of discussing this. One simplification we can make, and we will make in the next lecture, is if we set x naught or x0 to be 1 for each observation, we can simplify this further to being a sum that goes from j is equal to 0 to p of theta j xj. And the reason this is equivalent to this sum is because it's really just multiplying theta naught by 1 and replacing that 1 with an x0. And the reason we do that is to account for the intercept term in our model. This is the notation we will use moving forward for linear regression models. What I want you to do is try and think about how you could rewrite this sum in terms of a vector multiplication, which is something we will do in the next lecture and is something that you will need to be familiar with. So you might want to start thinking about how this relates to some linear algebra concepts. Now, one point I wanted to make was that, we're looking at these 2 models. One just uses assists as a feature, and one uses assists and 3-point attempts. You might notice that the coefficients are different in the 2 models. For example, the intercept term in one is 3.98, and the intercept term in the other is 2.163 or so. The coefficient on assists is 2.4 in the first model, and it's 1.64 in the second model. So generally, these will be different if we are using different models. These coefficients that we found are the coefficients that minimize average squared loss for these particular models. Right? The first model looks like theta naught plus theta 1x. The second model looks like theta naught plus theta 1x1 plus theta 2x2. Those are different models, and so the minimum value of their mean squared errors might be different, and their coefficients will likely be different as well. 2.4, for instance, is the slope of the relationship between assists and points when only looking at assists and points. 1.64 is the slope of the relationship between assists and points when also considering 3-point attempts. So I just want you to remember this. When we add or remove features, the coefficients will likely all change. To wrap up this video, I wanted to introduce a new piece of notation that we will often use moving forward in this class. You can see that our regression models are a function of some input variable x. Now, our simple linear regression model only had one input, x, which was a scalar, and the more general linear regression model has p inputs, x1, x2, x3, so on and so forth, through xp. Regardless, we can write these all as being a function of an input variable x. Our constant model from last lecture can be written as f sub theta of x is equal to theta. This subscript theta refers to the choice of model parameters that we are using to make our predictions. And so, for the constant model, the way we make our predictions is just by outputting theta. For the simple linear regression model, the way that we make our predictions is we take theta naught and add it to theta 1x. In the multiple linear regression case, which is what we are now looking at, the way we make our predictions is by taking x and applying this formula, this weighted sum of coefficients and x's. Now you'll notice in the latter two models, the subscript here was theta, but the coefficients that were actually a part of the model were theta naught, theta 1, theta 2, so on and so forth. And that's because theta is now actually a vector of coefficients, or a vector of parameters. In the last model, x is actually a vector as well. You can think of x as being a vector consisting of feature 1, feature 2, so on and so forth, through feature p. Don't worry too much about this right now. This is more just to give you a sense of where we are heading, but we will formalize all of this in the next lecture.